Hello, Doctor. I'm Rachel Rebecca. Today, me and my group mates going to present about experiment M2, which is the Hall effect. And my group mates are Siti Aisa and Suhaida. In this experiment, there is only one objective, which is to determine the carrier density and carrier mobility in germanium sample. The apparatus used in this experiment are germanium crystal Hall probe, Hall effect apparatus, electromagnet, constant current power supply, and digital gas meter. Here we included a picture of the setup of apparatus while we conducted the experiment. Now let's move to procedures. First, we connected the widthwise contacts to the Hall probe with germanium crystal to the terminal marked voltage and also connected the lengthwise contacts to the terminal marked current. And next we turned on the Hall effect apparatus and adjusted the current to a few milliamperes starting from zero point 0.5 milliamperes and continue with 1.0, 1.5 and so on. And third, we switch the display to the voltage side and observe some voltage reading even outside of the magnetic field. This was due to imperfect alignment of four contacts of Hall probe was generally known as zero field potential. We switched on the electromagnet power supply and adjusted the current to the desired value. And we aligned the Hall probe until it became perpendicular to the magnetic field. At this orientation, the Hall voltage was at its maximum. Then following by we recorded the Hall voltage for both direction of the current and magnetic field. This means we had four observations for a particular value of current and magnetic field. And we kept the magnetic field strength constant and measured the Hall voltage as a function of current. Followed by Hall voltage was measured as a function of magnetic field, keeping a suitable value of current as constant. And lastly, the magnetic field by Gauss meter was measured.
Hello, my name is Siti Aisa. So this is the data that we've got from the experiment for part 1, and this is the data that we got for part 2. This is the table that we've used to calculate gradient and also y-intercept. This is the analysis part that the calculation for gradient, and this is the calculation that we've done to get the y-intercept. And this is the calculation to get the accuracy for gradient and also for the y-intercept. So the gradient that we got from the calculation is negative 0.0389 plus minus 0.07924. And for the y-intercept, we got 37.116 plus minus 10.7369 volt. And this is the graph that we've plotted. So this is the calculation that we've got to get the Hall coefficient that we've got is 154.2416 meter cube over C. It is a p-type crystal since the Hall coefficient is positive, and this is the number 3 is calculation of charge carrier concentration of P, which is we got 4.0521 times 10 negative 16 meter cube. And this is the calculation of carrier mobility that we've got using the formula, which is we got 1542.416 meters squared volt per second. For question number one, what is Hall effect? Hall effect is the process of creating potential difference between the applied magnetic field that is perpendicular to the current and an electric current that is transverse to the conductor. It was discovered by Edwin Hall in 1879. What are N-type and P-type semiconductor? And for N-type semiconductor is a free electron majority carriers and holds the minority carriers. Meanwhile, p-type is holes are majority carriers and free electrons are the minority carriers. Question number 3. What is the effect of temperature on Hall coefficient is a lightly doped semiconductor? The mobility of charge carriers in a semiconductor decrease with increasing temperature due to increased lattice vibration and scattering processes. This can affect the overall conductivity of the material. The intrinsic carrier concentration of the semiconductor increases with temperature, affecting the overall behavior of the material. Question number 4. Do the holes actually move? No, they don't. The vacancy left by the electrons is known as holes. An electron hole is created by the atom's imperfect covalent bond which the surrounding electron fills. The electron leaves its original place as a hole after filling it. Next, the other electron that is nearby will fill the hole and disappear. This process will repeat again and again when it connects to the power source. Thus, the hole travels in the opposite direction of the electron's motion. For question number 5, it is shown that the carrier concentration of N that we've got. Question number 6. Why the resistance of the sample increases with the increases of magnetic field? The magnetor resistance is the cause of this. It is possible for the resistivity of an electrical device to change if a magnetic field is applied perpendicular across it. The current will pass through the electrical device in a straight line prior to the application of the magnetic field. After the magnetic field is applied, Lorentz force is exerted on the moving charge causes a deflection in the path traveled. This results in increased resistance and an increase in the path length. Question number 7. Why a high input impedance device is generally needed to measure a Hall voltage? It is to ensure the accuracy of the data. The high impedance device, such as voltmeter, draws the least amount of current allowed. Question number 8. Why the Hall voltage should be measured for both the direction of currents as well as magnetic field. It should be done to measure the Hall voltage more accurately and to acquire an average reading of the voltage. When a magnetic field is applied across a conductor and charges are separated into two edges, voltage is set up. This phenomenon is known as the thermoelectric effect. So that's all from me. Thank you.
Focusing on discussion part, what's the problem? Okay, here there is a limitation of the conductivity measurement. But at the first place, we have to know what is conductivity. Okay, conductivity is the ability of a material to pass an electric current, where it can be measured by passing an alternating electrical current between two electrodes that are immersed in a solution and measuring the voltage. Okay, so what is the conductivity measurement? Okay, conductivity measurement is a measure that only can measure the net current flow and resistance only, which is it can't measure the specific nature. However, in conductivity, there is a specific nature known as electron or hole or density of the charge carrier that actually contribute to the conductivity itself. Okay, so what are the limitations? Okay, the limitation here is conductivity measurement only can measure net force and resistance but not the density of the carrier and the carrier mobility. Okay, so what happened? Edwin Herbert Hall in 1879, he proposed a solution called the Hall effect to address this limitation, as I stated before. Okay, when a magnetic field is applied perpendicular to the current in a conductor, it deflects the charge carrier to one side, creating a transverse voltage called the voltage Hall. Hall voltage. Okay, so by measuring the Hall voltage, so from here we can determine the type, which is negative for electron and positive for hole, and density of the charge carrier. So this method provides crucial insight into the material electronic properties, which is enable us to differentiate between various charge carrier and a more detailed understanding of the material behavior. Question is, what happened in this experiment? Okay, what are the relation with the Hall effect itself? Okay, since we know that the Hall effect can determine the density of charge carrier and carrier mobility, so in this experiment, we try to prove, is it true? Is it really that the Hall effect can measure both as stated by using germanium? Okay, so what are the result is, we obtain Hall resistant majority charge carrier obtained is P type. Okay, so how we want to determine the majority charge carrier is by looking at the Hall resistance. If the value of Hall resistance is positive, therefore the majority charge carrier is P type. If the Hall resistance is negative, therefore the majority charge carrier is N type. So since RH in this experiment we obtain is positive, therefore we will focusing on P type. Okay, so P type value we obtain is as stated here, and then the carrier mobility also here, as you can see lah. Okay, to sum up, since we can determine the density of charge carrier, which is for P type, and the carrier mobility for P type in germanium, therefore the case is proven lah regarding to the Hall effect that was proposed by Edwin Herbert Hall in order to overcome the limitation of conductivity measurement. Okay, that's all from us. Thank you for your time. Thank you, doctor, and that's all from us.